Good afternoon on this Friday at the end of February. We are having as a topic, we have current sensors and achieving precision in current sensing, current measurement, and power measurement. I would quickly like to give you an outline of what we're going to do the next, well, they said 30 to 45 minutes. They don't know that I have a notorious tendency to overrun a little bit, but I'm trying my best. So we have, from the outline, I would quickly like to introduce Hioki as a company, but really only 1 or 2 minutes. Current measurement with direct input and shunt resistors is one of the topics that we're looking at, and then compare it also with current measurement with sensors. I would like to tell you, or basically put next to each other, the working areas of direct input versus current sensors in power measurement. That's very important. And then actually we would like to look a little bit at the challenges in high current, high frequency power measurement, which is something that you see more and more with the development of SiC and GaN applications. So about Hioki, as I said, 1 or 2 minutes maximum. Hioki is a test and measurement company. For everybody who, or for anyone who doesn't know, Hioki is a test and measurement company which is from Japan. It was founded in 1935. It has always been a test and measurement company. From day one, the first product was an electrical indicating meter, something you'd probably today call a multimeter. The company today has about 1,000 employees around the globe. The annual turnover is approximately 200 million euros. It always depends a little bit on the exchange rate with the Japanese yen, but ballpark, it's about 200 million. Hioki is very much driven by engineers. It's not a commercial company, as you see from other test and measurement companies as well, especially those from the US. Hioki is very much focusing on engineering and production, and all the products we make, or the main products we make, are made in Japan in our factory in Ueda, the Nagano prefecture, so in the area which are perfect for skiing. And where the air is dry, that's where they make test and measurement equipment. So the company Hioki has been founded in 1935, but we're actually only present in Europe with our own subsidiary since the year 2017. If you want to find out why it took so long before Hioki decided to open a subsidiary, then click on the link and you can find out a little bit more details about these things if you're interested. This is an overview of the portfolio that Hioki does. So Hioki does pretty much everything in test and measurement, from handheld digital multimeter to benchtop professional measuring instruments, as we call them, and automatic test equipment, which would typically go directly into production environments. We are primarily going to focus on current sensors today. Of course, we are going to also touch a little bit on power analyzers, because especially when it comes to SiC and GaN measurement, power analyzers are always involved, but the focus is definitely not on the power analyzer, but the focus is on the current sensors. So first of all, let's look at the typical way how to measure current, which is done with shunt resistors, which are very often found as a direct input option, be it in a digital multimeter or in a power analyzer. So in this example picture, you can see that the shunt resistor is in a power analyzer, but of course it's the same situation that you would find if it would be a digital multimeter. It could also be just an external shunt box. The principle of a shunt is the same. Shunts do have a very well known, and they are very well known, and they are a very accepted way to measure currents. The beautiful thing about shunts is that they are part of the measurement device. Again, it could be a power analyzer, it could also be a multimeter, it could, of course, also just be a certain shunt unit, but it's integrated. And shunts are absolutely great for small currents. The downside with shunts is a limited current range. There are self-heating and high-frequency leakages, which cause inaccuracies, and that's actually what I would like to look at in a second. And of course, the big downside of shunts is that you need to unconnect your DUT, your setup, and actually make the shunt and the measurement device part of your DUT basically. So your DUT becomes part of your entire system, and you definitely need to rewire things, which sometimes can be tricky. As I said, self-heating is one of the big topics that you need to look at when you're working with shunts. When you're working with small currents, there's absolutely no problem. Shunts don't heat up from small currents, but you very often see direct inputs, 10 amps, 20 amps, 30 amps. There is someone who actually even offers 50 amps direct input with a shunt. And then you have to see that there is an element of self-heating. And in this case, the picture, you can see the shunt. This is a 2 milliohm shunt. There's 20 amps of current being driven over it. And this image is taken after about 10 minutes. And originally, the temperature in the room was much lower, of course, than it was after 10 minutes. So the temperature increased by about 20, 25 degrees from room temperature to around 50 degrees of the shunt. Now, if you say, that's not a problem, shunts are still very precise with higher temperatures, especially when you consider manganese shunts, which is the typical material that are used nowadays for shunts. Yes, that's true. Manganese shunts have a very, very good temperature behavior or accuracy in regards to temperature. The only problem there is that this is only for the shunt material itself. It's not for the connectors that also heat up. It's not for the copper wiring around it that heats up. And that's the part that then causes the inaccuracies in your measurement. One of the big things that you also have with these kind of shunts, especially with manganese shunts as well, is that driving high currents over them speeds up aging, and it requires frequent adjustment to maintain the accuracy. Sometimes you can see with shunts when there is an instrument that has been adjusted, that you see that it's only a 3 months accuracy guaranteed or something like that. So more current, more self-heating, that's normal. It's the simple background behind that is a shunt is a resistor, and you have electrical power, which is P times voltage minus P equals voltage times current. And if you then take the law of Ohm, which is voltage equals resistance times current, and you replace that and put that into the power equation, then you have the power equals the resistance times the square of the current. That is nothing different than the Joule heating, completely irrespectively of the material. It's just simply the heating that starts that has to go away somewhere in that resistor, which is the Joule heating. And these kind of variations of the temperature, they of course they are a source of error. And the important bit is it's not only the resistor, the shunt material itself, it is the whole construction of it. Now, what you can do, of course, or what you have to do, if you use high currents in a shunt, what you have to do is you have to massively lower the resistance of the shunt. So, for example, because you have this square root in the formula, what you would typically do, if you want to produce the same heat in your shunt construction with 3 amps, if you want to produce the same amount of heat with 30 amps compared to 3 amps, then you basically have to reduce the shunt size from 100 milliohms to, say, 1 milliohm. So by a factor 100, you have to lower the resistance value if you increase the current that you want to drive through it by the factor of 10. That means that the shunt values are then very, very low. And that brings a different negative with it, which is a high frequency leakage effect. Effectively, every resistor has inductive and capacitive components. You just don't notice them if you use them if you have higher resistance values, but the lower the resistance value becomes or gets, and the higher the frequencies become that you're using with, the more important is the L values and the C values that you have to look at, the capacitance and the inductance. And in this case, what you can see is that there is an amplitude and a phase error that increases massively in the shunt. And that's actually the reason why shunts can be either used for high currents or for high frequencies, but typically not at the same time. So that is the downside with shunts. And so if we summarize that, basically, shunt resistor values, they vary with the temperature. You can use high current or high frequency shunt, but typically not the same, not at the same time. And the tricky bit is if you look at power applications nowadays, especially those with SiC and GaN, the frequencies are becoming higher and higher, and the currents are going up and up again. So that makes the usage of shunts for that application pretty tricky. But overall, shunts are absolutely great for small currents. If you're dealing with small currents in power measurement, shunts are a good solution for that. So let's look at sensors as an alternative, or as the alternative way of doing it. The big advantage of sensors is you have no physical contact with your DUT. There is no relevant self-heating effect, so you can use them for high currents as well. They're easy to install, especially when you look at clamp types. And in power measurement, and that's the downside of it, in power measurement, they're not suitable for really low currents of like 100 milliamps or less or something like that. And of course, and that is also a very important thing that you have to keep in mind, space is required to install the current sensors, because the bigger the current at the end of the day, the bigger the current sensor gets as well. So you need to have that space to put the current sensor in there. If you're looking at very, very small PCB layouts or something, like you want to measure the current going into a transistor or something like that directly or very close to the transistor, you're going to struggle with a big current sensor. Just to give you a little bit of an overview, what kind of current sensors there's typically around, we have about 3 different groups of current sensors. And one of them, they are the ones, the red ones you can see going up until about 10 megahertz as a maximum, suitable for power analysis. And then, of course, they're also going up to about 5,000 amps as a maximum. And on the other side, you see the ones that are typically used for debug and analysis of waveforms. That's the blue one. You can see that they actually are high bandwidth sensors. They go up to 100 megahertz. You can see that they go down to smallest currents of 100 microamps. So not even milliamps, but microamps. So they go down in currency very, very much. And then, of course, you have the typical AC commercial, or we call them for grid measurements, these kind of current sensors. That's the yellow ones in the graphics, and they are typically not made for super high frequencies and also not for super low currents. Just looking at them, I'm basically starting with them just to get them out of the way, if you want it like that. They are the typical technologies is Rogowski. You have simple hole sensors, or you have simple current transformer designs in that. They're either made for load currents, very large currents with the Rogowskis that don't bring the required accuracy with them. And they're also made for leak currents. Typically, the place where you find them is AC power logging or power quality analysis, because the accuracy and the flexibility there is absolutely fine. The second group of sensors are the power sensors, which are used for debug and analysis. They can be already used. There's current sensors, they start for currents from 200 microamps as the smallest current, and they go up to 30 amps at the same time. We have current sensors which can work up to 500 amps. With bandwidth of up to 2 megahertz. So in case you say, wow, that's the solution for my power analysis. Not really, because there's one downside in these kind of current sensors, is that typically current measurements, they go on for a little bit of time. And these current sensors they are typically, the sensor technology is based on magnetic flux canceling technologies, in combination with a Hall element. And the Hall element causes an offset drift, and that offset drift causes an inaccuracy in your measurement over a longer time. In theory, you could, of course, degauss them or demagnetize them, but you would have to do that after a certain period of time, which is too short for power measurement or power analysis. And that's why in power analysis, the sensors that are typically used are zero flux technologies with a flux gate. And they bring with them the possibility to do high accuracy power measurement or power analysis. The important part there is the frequencies, the bandwidths are not as high, but that's down to the fact that they don't have the Hall effect principle, but they have a flux gate system. The positive thing, they don't drift. And that is really something that you want to do, that you want to make sure that that's the case in power analysis. So one of the big differences probably between current sensors from Hioki and other current sensors, although there's other makers who make voltage outputs as well. Hioki sensors, they feature a voltage output. And that basically means that there is also a shunt resistor in the current sensor, because a shunt is the perfect way to make a current into a voltage. And the voltage is what you need if you want to sample the value with an ADC. So you always need to get the current into a voltage, the typical way and the proven way, and a good way is doing that with a shunt. But obviously, it is done with a shunt in a current. If it's done inside of the current sensor, of course, it is always a very, very small current that's driven over the shunt. And that, of course, is the same as if you would drive a very small current from current outputting sensor into the shunt of your measurement device. It's the same thing. In both cases, you use shunts. In one case, the shunt is in the measurement instrument. In our case, the shunt is always, if there is a shunt in the system, then the shunt is always in the current sensor. So why do I point out that there is this big difference between, or that you have to watch out with the shunt in the current sensor? Because at the end of the day, and I was trying to find an example that kind of sticks in your mind or sticks in your head, just to be able to think is, what am I trying to, how do I best explain it? And that's if you go into your kitchen and you look at cookware, and if you look at your home appliance, your hob in the kitchen, very, very often you see that the cookware is not aligned with the dimensions of home appliances. And in current sensing, or with current sensors, that's exactly the same thing. Current sensor output levels are typically not aligned with the input levels of analyzers, because current sensors are typically made by different companies than those who make the power analyzers or the devices to actually do the measurement. Hioki is actually the only difference with that. But if you have a current sensor and an analyzer or your measurement device from a different manufacturer, then there is a risk that a low sensor output level will increase the signal to noise ratio. And that, of course, has a negative impact on your measurement. So that is really something to look out for. And I've tried to bring this into a different picture, which is a bit more technical than the picture of the hob in our kitchen. And that is basically by looking at, if you take a sensor from Hioki, which outputs a voltage, the output voltage would be 1 volt. The maximum output voltage would be 1 volt for a 100 amp sensor, and that would be perfectly matched with the input of the ADC of our own analyzers. Now, we have taken an example, and actually I went to our graphics department. I said, can you draw this picture for me? Have the same current curve or the same waveform, and then have a smaller waveform below, and put them in different colors. And my colleague asked us, how much smaller do you want to have that smaller current? I said, take it factor 20 or something like that. That's typically the amount of value that's the kind of difference between if you use a matching system and an unmatched system. And then I actually had a look at a competitor setup, which is a competing brand of power analyzer and a different brand making the current sensor, which is a combination that you see not quite often, but you see definitely in the market. And if you compare that and you look at a 100 amp sensor with an output ratio of 500 to 1 in a combination with an 80 amp milliohms shunt of the competition's analyzer, then the voltage drop over the shunt is only 60 millivolt. And if you compare that with a solution that we do, where the Hioki sensor matches the Hioki current sensor levels, if that matches, then actually the factor is 60. So why I asked my marketing colleagues to make it factor 20, just to show the difference, really it should be factor 60. So imagine that red line would actually have to be much, much smaller and much, much more aligned than actually a curve. So that is a nice thing if you have current sensors and analyzers from, well, the same company. And I can say Hioki in this case because Hioki is the only company in the world that makes current sensors and power analyzers. So in this case, there is not a problem because the voltage signal output of the sensor will be optimized to match the ADC of the power analyzer. Of course, also the advantage of this solution is that the sensor is powered by the power analyzer under optimized conditions. And of course, there is an optimized noise protection. There is a voltage being transmitted. There is a voltage signal between the current sensor and the power analyzer. But you have to keep in mind that that wire is not only a twisted pair wire, but it's actually double shielded. So it's not only the signal wiring, the twisted pair signal wiring is shielded, but also the entire cable is shielded again. So this is very well protected against noise. And depending on the power analyzer you use, there's even an automatic detection of the sensor information. So that basically means if you plug in the current sensor from Hioki into a Hioki power analyzer, basically what the current sensor automatically does, it reads out the relevant information from the sensor, which in that case is the output ratio. And that's one of the most important things. It also reads out phase errors of the current sensor, but we're talking about that in a minute. So the next point is the working area of direct input versus current sensors. So we looked at direct input, or looked at shunts, and now we looked at the current sensors. Now let's put them together in another graph. The important part here is now we are comparing these for power measurement. We've seen before that there are sensors that can also go down very low with current, but again, they're not necessarily suited for power analysis. So if you look at power measurement, you can see very, very clearly here that there is nothing that beats the shunt in very, very low currents. On the other side, you have to say that when it comes to high currents, we're not stopping at 30 amps roughly, or maybe 50 amps, but we're actually stopping at 2000 amps. That is the big advantage and disadvantage depending on what kind of power measurement you do. If you do high current power measurement, go for current sensors. If you do low power measurement, very low power measurement, shunts do have an advantage. So we are, of course, going to focus a little bit on things with high frequency and high power, because that's the exciting things that happen at the moment with SiC and GaN. SiC and GaN is everywhere or coming up more and more, and it's the big buzzword for quite a while now. So, of course, we're also looking at that. And SiC and GaN applications do have a very, very big advantage, because what does SiC and GaN allow you to do? At the end of the day, the higher switching frequency allows you to decrease the size of your step-up reactor in your design. And the step-up reactor in your design actually allows you, if you have higher switching frequencies, or if as you can see on the right side of the screen, if the L can decrease, if the omega is a 2 pi f, which means the frequency inside of it, if the frequency goes up, the size of the inductance can go down, or the reactor can go down. And the beautiful thing for that, with that is, or the big advantage for that is, if you have these high-speed switching frequencies, that allows you to realize smaller builds. Smaller builds result in more freedom in design. It results in less resources being required. And of course, it increases the power density, because you have more power that you can achieve on less room. Just think about an electric car and the importance of doing things small. Think about an electric car in terms of having the freedom to make a design or to change a design to make it optimized for a car application, so for any other application. And that is the big advantage of SiC and GaN developments, or the SiC and GaN technology, basically. And that's why it's becoming more and more popular. And now it gets a bit more mathematical, but don't worry, it's not getting too much mathematical. There is a couple of things you have to look at if you're making measurements, especially with higher frequencies and higher currents. And that could be the current sensor, but it would also be a shunt. And the shunt has the same effects inside, or a shunt system has the same effects. You have to, at the end of the day, look at the same information or the same characteristics and specifications. And one very important thing is the amplitude error. Sometimes we also use the term gain error, but I use the word amplitude error here. So we've got the amplitude error and we've got the phase error. And now if you look at the calculation of AC power, that's voltage times current times the power factor, which is cosinus phi or phi or phi, I think it is. So in that formula, you have the two elements I, the current, and the cosinus phi, the power factor. And the amplitude error that you see in specifications for example, for current sensors, the amplitude error affects the I, while the phase error affects the power factor, the cosinus phi. That's just as a preamble before we dive into looking at the specifications a little bit. And now what you can see, here is a picture of the amplitude error. And then, of course, it becomes clear some current sensors are made for high frequencies and high currents, while others are probably only made for, let's say, more DC or lower frequency applications. And one of the things where you can see that here is you see, especially our flagship model CT6904 from Hioki in that graph. That is the violet graph. You can actually only see it at the very right side, at the very bottom right side of that graph, because it's basically a flat line. And that is the frequency behavior, it's the amplitude error over the frequency in percentage of reading. And what you can see that we have compared our sensors with sensors from two competitors, or two very popular sensors from two competitors. And you can see that one of them, which is actually widely used also for current measurement or for power measurement, is actually already has a huge dip at 16 kilohertz. 16 kilohertz, that's probably below the base frequency of a SecondGun application. Just to give you an idea where the big errors start, there is, you see that there is an 80% reading error already for the third harmonics for one of those sensors. And the third harmonics, if you have 80% reading inaccuracy, then of course you know that that measurement value is something you have to take very, very carefully, because if you have such kind of reading errors at such early frequencies, then in that case the sensor would not be suitable for the measurement that you're making. If we're talking high frequencies, if you're talking DC, no problem, everything is fine. And what we have also done is we looked at the amplitude and the phase error. And again, we have picked a very well-known competitor's product. So when we put products against each other, when we say this is us and this is the competition, we're not picking our best one and then take the worst 10-year or 20-year-old sensor from the competition, but we're looking at competitive sensors that are available today with the same characteristic advertised for the same application. And then we look at the data sheets of those, and you can see the left side is a copy of a data sheet from our sensor. The right side is a copy of a data sheet from a competitor sensor. And now it's important for me to highlight that when I copied that, when I did the screenshot of the competitor sensor, I didn't cut out anything on the right side. There is nothing happening on the right side. There is not a scale missing. There is not further data missing or anything like that. That's it. Nothing else is specified. And now just have a look at the frequency end of our specification and the frequency end of our competitor specification. You can see the competition actually stopped specifying amplitude and phase error already at 300 kilohertz. Again, that's the third harmonics if your base frequency, like in SiC, is 100 kilohertz. If you look at our sensor, then you can see that, we are actually going far into the megahertz areas in terms of specifying the bandwidth. So one thing that you also notice if you look at the phase error, if you compare the phase error from our sensor with the phase error from the competition, both are the reddish colored ones. You can see that the phase error in our sensor, in our premium high-end we've got it all sensor, actually starts earlier than in the competition. You can basically see that there is a phase delay starting at about 1 kilohertz. It slowly starts to dip off, and that's our sensor. That's the Hioki sensor. It's 1 kilohertz. You already start to see a phase delay. So how come we tell you, this is the best sensor, when on the right side, our competition, you can say that the, 10, 20, 30 kilohertz, 40 kilohertz, you start to see a phase error starting to take off at about 30 kilohertz. In our sensor, it starts at 1 kilohertz. And I'm using that as a reference. It's like, it's not really advertising, is it? But there is a technical reason for that. And I would like to explain that technical reason to you. And the reason is that the time delay, which is the base for the phase error, the time delay of our sensor is exactly the same over the whole frequency band. Or it's almost the same. And in this case, it's a very, very good, it's like basically a line. So if the time delay is similar over the whole frequency band, of course, you will see something starting constantly earlier than with something that has no time delay at the beginning, and then all of a sudden it starts to really dip away. So that's the reason why in that phase curve, you can see that there is a more constant decline, or there is a more constant increase in phase error in our sensor or not. And why is it so important for Hioki to have this time delay in a very constant way? And what is actually the time delay? And if you look at the time delay, I always use the example of an oscilloscope. An oscilloscope, 2 channels. If you want to match the signals coming into 2 channels of an oscilloscope, you have a DESQ function, because you might have latencies in a sensor, and that's exactly what we're talking about. There is a latency in the sensor. In our case, it's a constant latency, which is frequency independent. And then you have the DESQ function in that oscilloscope, and that allows you to basically bring those things together. And that's exactly what we can also do, because we have this constant time delay. And that basically allows us, if you translate it again, if we have this correction value of 100 nanoseconds in that case, we can apply it for every frequency. And 100 nanoseconds at a very low frequency is nothing. At a very high frequency, of course, it makes a big difference. So that the fact that we have the same time delay over the whole frequency band, that allows us with one single correction value to actually correct this phase delay or phase error that is caused by our sensor circuitry. And that's the big thing, what we call phase shift correction, because that is a feature that we have in our power analyzers as well. So basically the power analyzer knows which sensor is being used, and it knows the error of that sensor, this constant phase delay of the sensor, and that allows us to basically make that correction with just one value. And that's why I said it's like Hioki has this constant time delay. If you compare this again with competitions, it's the same sensors that we used before, both very popular, and they are specified to be used for this kind of measurements. If you look at the phase delay that you can see the time delay, you can see that this is not a constant time delay, and that has the effect that one single value is not going to be suitable to make any kind of correction. So basically phase correction as we do it will not work with that. And you can see from the Hioki sensors, and that's really where it matters, you can see that there is almost a constant time delay between 5 kilohertz and 1 megahertz. So the 5 kilohertz, that's where it really matters in power analysis for higher frequencies. And to be honest, at 1 kilohertz, the time delay of 100, or the jitter that you see at 100 milliseconds, it doesn't really make a difference. So summarizing phase shift correction, this is the PW8001 power analyzer. It actually reads out the sensor's compensation value automatically when you plug it in. So as it reads out the serial number and the conversion ratio, or the voltage ratio, it also reads out the phase shift correction value, and that's what we call automatic phase shift correction in our PW8001 power analyzer. If you want to have a look at how the competition is handling phase shift correction, this is a link, or there is a link, it's to a LinkedIn post And on that LinkedIn post, you can see how the competition is doing that, but only for actually a single frequency, because that setup will only work for a single frequency. But you can see what you need in terms of equipment if you want to do that, if you want to tackle this issue with the competition. And on the contrast with us, it's just plug and play. And if you want to find out more about the topic, phase shift correction, then there is also another article page. It's also a LinkedIn, which is called It Takes Two to Tango. And now let's have a little bit of a look at a reactor measurement as an example. And again, why is this so important? A reactor is an inductive element, and we're using the same graphic on the top left as we did before. It's a simplified circuit of an electric powertrain. And you see this big step-up reactor, you see this SecondGun smaller step-up reactor with the high frequencies. And if you want to measure that reactor, which is an inductive element, you always deal with low power factor parts in this power measurement, especially when the frequencies are high. And then if you look at the right graphic, then you can see if you're dealing with a high power factor, then the phase error actually has a very, very little impact on the active power value that you measure. But if the power factor is very low and you're dealing very closely to the inductive side of this typical P and Q diagram, if your power factor is very low, which means your phase angle is about 90 degrees or close to 90 degrees, then any kind of change in the phase error, and the phase error having an impact on the angle that you measure, has a big impact on the active power measurement that you do, and that will cause a measurement error and inaccuracies. And that's actually especially why for these kind of SiC-and-GaN measurements, why for this kind of step-up reactor measurements, all these kind of things, why it's so important to have this phase shift correction function and to have suitable sensors that are also capable of dealing with the frequencies that you're looking at. Because of course, you're not only looking at the base switching frequency, you have to look at harmonics as well, or you do look at harmonics as well in your measurement. So just summing that up, internal shunt resistors, they are the best choice for very low current measurement in power analysis. They are a very, very good and very sound and valid choice for low current measurements. That's why many Hioki current sensors use shunts as well. So shunts are not bad as such. The question is just, are they useful for higher currencies, for higher currents and higher frequencies? And what I try to explain in these slides is that they're not ideal for high current and high frequency applications, simply because of the design of shunts, either with heat or with the high frequencies. One of the things that is important is you should make sure that your current sensor output and your power analyzer input have aligned levels. So even if you use current sensors and power analyzers, not from Hioki, which is absolutely fine, if you use them, you need to make sure that the sensor you pick is matching the input, the ADC input and the shunt value of your current, of your power analyzer. These things have to match. You can have the best power analyzer, which boasts with a super great accuracy. If at the end of the day, the signal that you put in from your current sensor is super low, your signal to noise ratio is far too low, and you need to have a high signal to noise ratio and not a very low one. So from that point of view, that is really something to look at. Of course, if you use a Hioki system, in that case, you don't have that issue because Hioki takes care of that for you by making sure that the current sensors and the power analyzers work with each other perfectly. It's actually the reason why you cannot use a third-party current sensor with a power analyzer from Hioki. It's one of the reasons. So choose the current sensor which has the correct frequency characteristics if you're working with high frequency. You've just seen in the pictures, you need to have, if you're looking at frequencies of 100 kilohertz, switching frequencies of 100 kilohertz, there is no need to look at a current sensor that stops where the specification ends at 300 kilohertz, because that's just covering your third harmonics, and that's nothing. While at the same time, the power analyzer that you would use it for boasts that it can measure up to like 500 harmonics. when after the third harmonics, your current sensor doesn't provide adequate data, where's the point, basically? Very important, keep in mind the phase error when dealing with high currents and high frequency applications. It is a phenomenon that you have with every current sensor, and you actually also have it with shunts, but especially with high power, high current applications, the power and the current sensors, you need to keep in mind the phase error that you're creating. And that phase error is like a physical phenomenon. It's nothing that you can reduce to zero. Only in the physics book at school, the current sensor or this kind of measurement doesn't have a phase error. But in reality, it's a physical phenomenon. You cannot avoid it. So every current sensor has that. The question is, how well is this phenomenon dealt with, basically? And with the Hioki solutions, of course, especially phase shift correction allows to compensate this phase error caused by every sensor in the world. And I think that's it from my side. I think I haven't overrun that much. I don't know if there is still anybody there. You might have all switched off and went home because it's Friday. Oliver, you're muted.
Yes, so as we say in Germany, it's a Punktlandung, I would say, right on spot, time-wise. Congratulations, Kai.
Thank you.
Thank you very much. So far, I have one comment in the chat, but no questions at this moment. So my question to everybody listening so far, and we only have a few people left so far, is there any questions? Are there any Are there any questions at this point? I mean, if it's not right now, or if it's not the right tool to put it here in the Q&A function, of course, we have other ways per email or so. If you follow up with us, you can ask questions outside of this. But if there's a question right now, you say like, hey, what was this about? Or what is the meaning of that? There's one thing coming up.
Yes, there is a question, but I'm checking the chat in the background.
Exactly. So now there's a question from Mr. Friedrich Stork, who says, how do you achieve the constant phase error in your sensor design?
We are not going to tell you. That's magic. But that actually is the engineering. That is the engineering design. That's the design behind it. Giving you the blueprint here, or talking to you, saying the blueprint. First of all, I don't know exactly because not even our Japanese headquarters telling that to us. But there is no way, even if I would know that we would share how we actually achieve that. But it is actually design. It is by design, and there is also, from what I understand, I mean, you can see that the phase error starts much earlier than somewhere else to make sure that it can be corrected, that the phase delay is constant. So there is some almost, let's say, artificial tweaking to have this constant error, because with the lower frequencies, of course, it wouldn't be necessary to have this kind of error. But especially with that CT6904 sensor, it's very much like the sensor is tweaked to have a certain error. Even if there wouldn't be an error by design, it gets an artificial error to make sure that this phase delay is constant. But at the end of the day, of course, that's the big engineering know-how of Hioki to make sensors in that way. And I think if I would look at Hioki products, then the current sensors, I think that's what we're really known for in the world, for the high quality current sensors that we make.
All right, thank you for that.
Perform with regards to phase error, that really depends on the shunt value that you're using. Because again, if you're using a very, very small resistance value, your phase error will be higher. So it really depends on the shunt values and definition. Shunts in general are not a bad thing. That's really, I'm really trying to highlight that, or I tried to highlight that a couple of times. Hioki never uses shunts in the power analyzers, but we also use shunts, of course, in the current sensors. And the important thing you have to keep in mind, if your shunt is in your power analyzer and it's not in the current sensor, when we specify a current sensor, then the inaccuracy of the shunt is included in that specification. If you take a current sensor, which outputs a current, where the shunt is in the power analyzer, then you have two inaccuracies. You have the inaccuracy of the current sensor, and you have the inaccuracy of the shunt inside of your power analyzer. But you cannot say, how do they perform? They have the same effect. It's a physical phenomenon. You cannot avoid it. And it really depends on what, basically, I would say take a manual of the competition from a power analyzer, which have shunts, which use shunts or internal shunts as measurement, and have a look at it, whether they specify it. I actually don't know whether they specified and how they specified. Sorry,
Okay.
so I don't have a super good answer for that.
All right, so there were two questions, two answers, well, one answer and one comment.
I have one. Yes.
Are there any more questions?
Yes, we can share the PowerPoint, by the way. Of course, we will share the PowerPoint. If you're registered, then basically our marketing colleagues will send out the PowerPoint. You just have to make sure that if you use a Gmail address, that it doesn't end in a spam filter or something like that. But yes, of course, we share the PowerPoint with you. How many current probes you have with automatic phase correction with new analyzer? Since the end of last year, we basically revamped our current sensors. So many current sensors that you have that are called CT6845. Since the end of last year, new models were introduced, and they're called CT6845A. And if they have an A, then they are able to provide, then they're able to communicate the phase correction information with the power analyzer PW8001. But it doesn't mean that you have to throw away your old sensors, because your old sensors have a fixed value. All you have to do is take that fixed value that you know that information comes with the current sensor, and you just have to manually add it into the power analyzer. It's just one value that you have to enter as a phase shift correction value. So you don't have to change anything if you have the old ones. There is absolutely no, I would never, I mean, of course, being sales, it's great if you throw away the old ones and buy them in new, but to be honest, for that change, I wouldn't do that. It's just that the A versions have the automatic information, they support the automatic information, but you can always enter this value manually. It's not a problem. What needs to calibrate this current sensors? I have to say, I don't really understand that question. You need to have the right calibration lab, I would say, that is able to do that, because one of the big magic is calibrating power. You have a lot of calibration labs that can calibrate voltage, and you have a lot of them that can calibrate current, ideally with a power factor 1. And you need to find the right calibration lab that actually can do that. But other than that, there is nothing special required for that. Is Hioki the only company used in the range certification of EV and PHEV? If so, why? Okay. Good question. Is Hioki the only company used in the range certification of EV and PHEV? First of all, I don't know if we are the only ones. I know that we are widely used in that area. And one of the reasons is that we have clamp type sensors. A lot of the certifications that you're talking about, range certifications, they measure the battery output, which is DC. And for DC, you don't usually use push-through, or you don't need to use push-through sensors, but you can use clamp sensors. Difference between clamp sensors and push-through sensors is the clamp sensors, they are a little bit less accurate, but they are, of course, easier to apply, because imagine you have an electric vehicle and you want to do a certification. The vehicle comes in ready. You're not able to strip off the cables to put a sensor through. So you need to have a clamp type sensor with a very, very high accuracy. And I'm not aware that there's anybody else who does sensors with the same accuracy as Hioki does them. And that's the reason why very, very often you see Hioki sensors for this application. But I honestly don't know if we're the only ones. I know that we're widely used. You can find pictures of very famous electric cars being measured, and you can see the Hioki sensors being used, but I cannot tell you if we are actually the only ones. Widely used, yes. And the reason is simply because we have clamps. Hang on. Shunts perform a phase error. How we can change the bandwidth of a current sensor if you want to switch in frequency. Oh, you don't? Okay. Okay. So there, okay, let me read that question now. How can we change the bandwidth of current sensor if you want to change the switching frequency? You don't change the bandwidth. The bandwidth of the current sensor is specified from the beginning, and there is no ADC inside of the current sensor. There is effectively also a shunt that creates an output value, but there is no kind of sampling frequency that you have to take care of. The current sensor comes with a specified bandwidth, and whether your switching frequency is 1 kilohertz, 10 kilohertz, 100 kilohertz, or 1 megahertz, it doesn't have an impact on the bandwidth. The bandwidth of the sensor is independent to your switching frequency. I hope it does answer the question. If it doesn't, please get back to us or get back to me as well. Is it passable outside the factory? Sorry, I don't understand this question. I have to say, what voltage ranges do you have in new analyzer? 1500 volts Cat2, and that's the very important thing. 1500 volt Cat2 is the DC voltage input of the PW8001 power sensor. Why is the Cat2 so important? Because there is a standard that has changed and that requires to make these kind of measurements in a Cat2 environment. And that's why the PW8001 power analyzer has 1500 volts as Cat2. PW6001, the predecessor, smaller brother, whatever you want to call it, you can also drive it with 1500 volts DC, but not in a Cat2 specification. So if Cat2 specification is important, PW8001 is the answer. I'm not aware that there is currently another power analyzer which has Cat2 on 1500 volts. I think the others only have 1000 volts, but I'm not 100% sure here. Okay. I'm trying to go. This is a little bit of chat question. I'm actually also going through the chat.
Yes, there's now 2 questions also coming up in the question and answer right now. 2 more. Is Hioki the only company used in the range of we had?
That's what I answered.
Yes.
That's what I tried to answer a second ago. What about the questions in the chat? I'm trying to follow up with the questions in the chat. Please feel free otherwise to copy the question from the chat into the questions and answers, because actually following up in the chat is quite difficult because there's a lot of communication going on between people. So it's a lot of scrolling around and trying to catch it. That's why we're actually asking, please use the questions and answers, because when people use the chat function, actually do interactions, it's really, really difficult to copy that. Hang on a second. I just see your name. What is the maximum diameter of the low current measurement, for example, the Rogowski one? Of the low current. I have to honestly check in. Okay, which is the maximum diameter of the low current measurement, for example, the Rogowski one? So Rogowski is something you should not necessarily use for power measurements simply because of the accuracy. Also, don't forget that Rogowski is typically an AC measurement, typically. Which is the max diameter? I need to check back on that. In the slides, there is my contact details. I can actually you should see them now. You should see my contact details, both email address and LinkedIn contact. If there is a question you have that I didn't answer the way you want to, or I didn't probably get it correctly, or if I misunderstood the question, please just get in touch. And of course, I get back to you. So I'm trying to find other.
There's one more question that we have in the question section, which is, do these current sensors lose their calibration if current is ran through them without power supply connected to sensors?
These sensors lose their calibration if current is run through them without power supply connected to sensors. I'm pretty sure no. But we have to check that. I will check that with my engineering colleagues. It's an interesting question, which I haven't heard before. I think no. It depends on the, I can see where the question comes from. It's an interesting question. Do these sensors lose their calibration if current is run through them without power supply connected to sensors? I don't think so, but I will check that and get back to you as soon as possible. If for some reason I lose the chat question or the contact details and you don't hear from me within the next 48 hours, please ping me on LinkedIn or send me a quick email on kai@hioki.eu, because in that case I just lost, the question has just gone lost, or your contact details have gone lost. I don't know if that happens with...
We try not to. We try to keep up.
Try not to, but
follow.
If I don't answer to you, then very likely it's a technical reason. Catch something. So I will check.
We have one more.
I will check with our. Hang on a second.
There's one more question.
See, actually, there is also actually questions and answers going on in parallel in the chat, because we have two engineering colleagues who are taking part in the question or in the chat discussion as well, which wasn't planned, but it's an interesting conversation going on there. Hida, if you hear this, can you help me with the question, do these current sensors lose their calibration if current is ran through them without power supply connected to sensors? Hida, our Japanese Wikipedia from Hioki Europe, the man who knows everything. Maybe you have the answer in your mind. Otherwise, Kimmo, we will follow up on this one. And I'm just taking a screenshot, trying to take a screenshot of this one. Do we have other questions? What is the best sensor to measure leak currents in a sprinkler system, for example, over the pipes? The leak current of sprinkler systems, I would definitely say one of our leak current sensors or leak clamp meters, probably even CM4002 or 3. CM4002 or 3. It is, again, something that we can get back to you and send you the answer by email. Also, again, if you have very specific questions in terms of details, what you actually want to achieve, always get in touch either with us, get in touch with our sales partners. Hioki has sales partners all over Europe, which actually have a lot of know-how as well about our products. But of course, always feel free to get in touch with us directly.
You want to type? Okay, one more question from Mr. Uwe Reuschenbach. Is there a significant effect on the alignment from the sensor to the cable? Let's say it's not 100%, but at 90% to the cable.
No, not with
90 degrees to the cable, sorry.
Not with Hioki. I know that there is this is an issue, and I know the DIY solutions that are sometimes being used to prevent this problem, but this is not a problem with Hioki sensors. And actually, it's a fact that it's almost impossible to achieve. Imagine you make a measurement in a car with a clamp. You won't believe what happens to the clamps sometimes, how they are squeezed in to actually fit there. There is no way that you have laboratory measurement conditions of 90 degrees of the cable going through it, but it's not a problem. Effects of conductor position, stable, high reproducible sensing in general. Daniel, my colleague, thank you very much. So I can see that basically the majority of Hioki Europe colleagues is half of the sales teams is here, and half of our product managers are taking care as well. But I honestly have to say I can't remember when we have had so many questions in a webinar. So that's really cool for us. Yeah. Because the worst thing that can happen if you make a webinar, if you put in the preparation time into such a webinar, and then at the end of the day you talk for 40 minutes and there's no question, that's pretty depressing actually, because it basically means that nobody really, well, was convinced, or you didn't take the people with you and actually couldn't provide information. So getting questions for us is always great.
Yes. But either way, I mean, this is still also we're still with the majority of participants are still with us. It's really, really amazing. Thanks very much for your strong interest. Thanks for all the questions. As Kai just mentioned, it's really great to have this kind of exchange ongoing for this topic. Other questions are still welcome. As seen on the slide, like we have the contact, you have the contact information from Kai or from a Hioki team that you have. Please contact us about the webinar and let us have your questions about this topic or others, but especially about this webinar here, and we will follow up on them. We will get back to you. Yeah. So, yeah, so we have an hour right now. We had a very good on-time presentation. No, thumbs up for that. And very good, very vivid question and answers. Thanks for that. Also for all participants.
Oliver doesn't stop to highlight that I was in time, right? Thanks.
That has to be mentioned. And yes, thank you very much for your participation. Thanks, Kai, for the explanations, for the good insights, for the logic to bring us through this topic. And yes, we will follow up as a team from Hioki Europe to your questions. You're welcome.
Thanks a lot. Thanks a lot for participating. And have a very nice weekend. Any questions again, just get in touch. No problem. We get back to you. Thanks a lot.
Thank you very much. Have a good weekend. Goodbye.
Thank you. Bye-bye.